tell you something about infinity Laplacians like that. Okay. Now, you know, I'm gonna just use a mean value theorem or Taylor's expansion if you like. So sup of gamma, I'm gonna divide everything by epsilon, gamma t equal to x. So remember that x is actually gamma t, so u gamma t minus u gamma t minus epsilon, t minus epsilon divided by epsilon. Plus 1 over epsilon, the integral from t minus epsilon to t, L gamma s, gamma dot s ds is equal to 0. Okay? Now, mean value theorem or differentiation rule whatsoever. So this equal to what? This is like derivative in t, right? And s1 goes to 0. It's derivative in t, so the supremum of gamma t equal to x. Differentiate on the first law, I'm going to have du dot with gamma dot t. Right? Differentiate in the second slot, I'm going to have ut. Nothing wrong. Okay. This is the average of the integral. So mean value theorem whatsoever is equal to minus. Yes. Minus. Yeah, mean value theorem, let's say, is equal to gamma t, gamma dot t. Okay, this looks pretty cool. I mean, so remember that gamma dot t can be anything, right? So let's say it's sup over gamma. I mean that sup of gamma dot t can be anything. So gamma dot t, I'm going to let it equal to q, and q can be anything. So sup of q in Rn of what? Ut. I switch the two things. Plus du dot q minus L gamma x is equal to gamma t equal to x cubed. Oh, what is this? This is the Lejeune transform of the Lagrangian, which is going to be Hamiltonian. So sum of this is going to be the Hamiltonian, so ut plus a x du. Now, where's the book, right? So in the sense of convex Hamiltonian, viscosity solution coincides with optimal control formula. And actually, this optimal control formula is being using a lot by the Italian school. They only care, well, not really care, but they care more about the neat properties of the parts. By the Italian school who study optimal control, like from Padova, like some of the guys know, or the French school, like Fatih school, that they only care about optimal control formula, because when you work with convex Hamiltonian, you say, wow, I have the formula, I don't need this solution. It's like this, and then it also agrees with the notion of variational solution by Viterbo school when H is convex. When H is convex and we have duality. So everything is agreed. But when H is not convex, everything is not very standard, it's not known. Not known for neat properties. Okay. So now let's have fun. I know that is the end, so
Because if you see the two things are the same, the sub over all gamma, so the gamma t equals x, and the sub over all q.
yes. Yes. Yeah, the set. Because here we localize the problem instead of looking at all the curves now. Yes. So this is a quick. This time t minus epsilon. So that's why some of you have to make this rigorous. So x. So the curves, if we localize it, we start here and basically we we claim that, you know, if we keep localizing it, the thing is that it's allowed to have any slope at the beginning, which is Q. The slope gamma dot at the beginning, and we require when we let f of this. But you know, you have to prove this this afternoon. What you need to do is take a test function and recreate the viscosity solution definition. But remember that when you replace this one by smooth test function, everything gonna follow because you can just do Taylor expansion and stuff like that. That's it. Okay, but keep this problem in your mind. That's what we do this afternoon. I mean, not always. Okay. So now, and also recently there are some results. For example, between here and I, that for example we can do some kind of also optimal control problem when we're switching to have some kind of system like this. So it's sort of like, you know, you can say like this, you know, assume that you drive on the street on the crowded road. You know, the problem here is sort of like you have to minimize the cost, but it doesn't say that you have to switch the mode of driving. You know, if it's too crowded, you have to switch it back, you know, to a different mode of driving. Or if it's sort of less crowded, you have a different mode of driving. So if you are doing switching between modes, you're gonna have some system. But I don't think I have how far. But you know, let's do something interesting now. Maybe I'm doing too much. What's that? Let me introduce a type of one again and infinity Laplacian. So of one and infinity Laplacian. Okay. Infinity Laplacian is known for a long time by Aronson and type of one infinity Laplacian. The connection was done recently by the paper by the group of Perez, Stram, and Jewel Perez, and then Stram and Wilson. But I don't think that that's not the right direction. Okay, so how to play the game? How to derive kind of fancy ODE from that? So by the way, infinity Laplacian is this equation. Infinity Laplacian is uxi, uxj, uxi, xj equals to 0. Here I'm using Einstein sort of conventional notation. Here's the repeated sum for I and j. I mentioned this because this is one of the most fascinating problems in the field that sort of the regularity problem is very hard. So the open question is the following. Is U is in C1 for any in Rn? For U in R? Is U is in C1? It's open. Is U is in C1 alpha? It's also open. So Ovidiu Sabin proved, Sabin and Sabin Evans proved that this is correct when the dimension is 2 and then there's some partial result for higher dimension. Okay, so how to play the game? It's very simple. So let's say I have a domain. I have two people stand here. Okay. Let's say I have this domain and I have on the boundary I put some boundary condition g of x on the boundary. So two persons are gonna always stay together, and then they're gonna move together. The game gonna end when they move to the boundary. Let's say in the room, it's gonna end when they exit the room. So is the non-zero is a zero-sum game between player 1 and player 2. Let's say if I exit the room at this z at x0, then player 1 gains g of x0 and then player 2 lose g of x0. So, for example, if I exit the room here, player 2 has to pay player 1 this amount. So Just again. Okay. So now how we start again? So this is the initial location. Now you throw a fair coin. Just throw it. Let's say it head, player 1 moves. If it's tail, player 2 moves. Okay. So you are given epsilon greater than 0. So epsilon greater than 0 here. So throw a fair coin. If head and 1 move, 1 moves. If it's tail and 2 moves. Just throw a fair coin. And a single move. And 1 moves inside the ball of the location, the closed ball of the location with radius epsilon. So you can imagine if the 1 is the guy who wants to win the most. So here, if you throw fair points, the guy who wants to win the most is going to try to move to the place where you're close to a high value on the boundary. While the second guy is the one who wants to lose the least, right? So you're going to try to move to a location that sort of could. So this is, let's say, the maximum value. This is a minimum value. Of course, the first guy wants to move to the maximum value, while the second guy wants to move to the minimum value, right? They have to take the less, right? The least. Okay. So that's sort of the game. So, because I'm a little bit unfamiliar at this moment because it takes a while to get used to differential game and I'm not doing an explanation. But like Gauman idea, we're going to define for x in the set U, we're going to define U of x to be the expected payoff that the player 1 will get. Let's say, okay, that's the expected payoff. Let's say, if we start at that point, we know that 1 is going to get some money.